Mathematics is the language of the laws of the universe. You are just a human. Mathematics is never going to make sense to you. The universe will never make sense to you. Science is not about making sense of the universe. Science is about observing the universe as it is and constructing models with powers of prediction. You must be very careful not to be biased by what you think makes sense or what you think is logical. That is not science. That is not mathematics. That is hubris. Aging is the rise in the risk of death due to intrinsic causes. Aging is a fact for almost all animals, both in the wild and in the lab. For almost all animals, death comes to the chronologically old disproportionately. But this need not be the case. Organisms could grow less prone to mortality with each passing year, just as many turtles grow stronger and hardier and more fertile with each passing year. You might be tempted to ask, why do we age? This is a good question. In fact, why do most organisms age is the most important open question in biology. However, you must be careful not to get caught up in the why of aging. What is a man doing when he asks why? He is shouting, "Make it make sense! It doesn't make sense to me!" Rather than asking the universe to conform to your human understanding, you should instead focus on observing the how of aging in order to develop effective therapeutics. There are two schools of thought on how aging happens. The first school argues that aging is caused by a passive accumulation of damage. This school contends that the body is trying its best to survive, but damage accumulates nonetheless. This school prescribes working with the body by developing therapeutics that clear damage at the cellular level. This is hard and has yet to yield any results despite a tremendous amount of effort. Luckily, classifying and clearing damage might be unnecessary. The body might already have the ability to clear any damage that has accumulated. A second school of thought on how aging happens contends that aging is the result of active self-destruction pathways. The second school of thought argues that the body is not trying its best to survive, and therapeutics should be developed with the goal of interfering with the body's chemical pathways rather than working with the body. The most effective methods of extending animal lifespan: caloric restriction, exercise, young blood transfusions, castration, and knocking out certain genes all revolve around disrupting the body's active pathways, rather than cooperating with the body or clearing damage. Remarkably, old organisms are rejuvenated by young blood, and old blood is toxic to the young organisms. For male organisms, castration leads to significant life extension in worms, flies, mice, and men. Young blood transfusions and castration lead to life extension by interfering with active pathways, not by clearing damage. Two other life extension mechanisms are exercise and caloric restriction. No presently available therapeutic or medical technology has shown anywhere near the same effects at extending lifespan as strenuous exercise and drastic caloric restriction. A responsible physician would tell you this. Caloric restriction and exercise lead to life extension by tricking the body into thinking it is in an adverse environment, not by working with the body. Anything your body does in response to exercise and caloric restriction, it could do in well-fed and less active conditions. However, your body is not trying its best to survive. Your body performs best only when it's tricked into thinking there is no risk of overpopulation, or is tricked into thinking there is a high risk of death from external causes. Extension of life in the presence of stressors is only possible because the body's holding some of its abilities in reserve. It follows that the body is not evolved to live as long as possible. Evolution has selected for aging, and the rate of death is being carefully modulated by evolution. Aging genes have been discovered in every organism in which they have been sought. A gene is classified as an aging gene if the organism lives longer when the gene is knocked out. Examples of aging genes are DAF2 in nematodes, and components of the dream complex in mice. These genes are components of active chemical pathways that have been evolutionarily conserved across various species. These aging genes have an ancient origin. They have homologs in organisms across the tree of life, going back to the simplest eukaryotes. Evolution has preserved these aging genes with the same conservatism as it has preserved the core metabolic functions essential to all life. Evolution has selected for active self-destruction. This is how aging happens. The weight of scientific evidence leans towards aging being an active process of self-destruction. However, this perspective is widely disregarded due to researchers asking why. Researchers struggle to make sense of the idea of evolution selecting for self-destruction. Active self-destruction does not make sense to them. But the truth does not need to make sense to them. Science is radically empirical. It is nature, not what you think makes sense, that gets the last word. Nature is telling us that having more offspring is just one aspect of fitness. Many researchers who believe that aging results from a passive accumulation of damage reject the notion that aging occurs significantly in the wild. They argue that evolution has had limited incentive to select for mechanisms to prevent aging since organisms in the wild face high external mortality risks, such as predation and disease. However, empirical evidence gathered for over more than a century challenges this perspective. Field studies have demonstrated that aging is, in fact, a prominent cause of death in the wild. Long-term observations of animal populations, like gazelles, reveal survival curves with a downward concavity, indicating that death disproportionately affects chronologically older individuals. Even when an animal falls prey to a predator, careful tracking shows that an aging-related decline, such as decreased speed and strength, are the reason these animals were at the back of the pack when the lion attacked. The cause of death of animal populations with concave downward survival curves should be attributed to aging, not to external mortality. Consider, for example, the polar bears. Long-term studies of polar bear populations take a tremendous amount of time and effort to complete because polar bears live long lives in harsh environments. However, the studies we do have show that older polar bears face a disproportionately higher risk of death compared to their younger counterparts. Therefore, the primary cause of death of polar bears in the wild is aging, not damage from their harsh environment. It is a common erroneous belief among researchers that many behaviors observed in laboratory settings are merely artifacts of captivity. For instance, there is a belief among researchers that obesity and wheel running in laboratory rats are products of their captivity. This, however, is not what we observe in nature. When running wheels are placed in nature, they are frequently used by wild mice even when no extrinsic reward is provided. Animals in the wild often become obese even when they have to compete for food. It is nature, not what you think makes sense, that always gets the last word. What we observe in nature is that aging is a prominent cause of death in the wild. It is simply not true that evolution had no incentive to select for longevity. Evolution had a high incentive to select for mechanisms to prevent aging. Evolution, however, chose not to select for longevity. Rather, it consistently selected for self-destruction. This is the how of aging. Researchers who understand that aging is an active process of self-destruction have different theories on why we age. Many researchers argue that aging itself may not have been a direct target of natural selection. This is analogous to evolution indirectly selecting for non-functional nipples in male humans. The male nipple was not the direct target of evolution. Evolution wanted to select for nipples in females and, due to the specifics of embryology, selected for nipples in males as well. Similarly, many researchers propose that evolution did not want to select for aging directly, but aging evolved as a compromise due to fundamental trade-offs between longevity and other vital traits. For example, the disposable soma theory of aging posits a fundamental trade-off between fertility and longevity. According to this theory, evolution has struck a balance between investing food energy for the future by keeping the body in good repair and investing the same energy in the present by producing more babies. However, there has been no evidence of a trade-off between longevity and any other vital trait in practice. When the body is supplied with abundant food energy and thus has the option of doing both a good job of repair and simultaneously producing a bountiful crop of offspring, this is precisely when lifespans are shortest. It seems there was never a trade-off after all. When we consider the broad variety of aging phenotypes in nature, it is clear that each one of the so-called trade-offs is surmounted in some organism. The Myotis brantii bat can live well over 30 years, while the Melosis bat has a lifespan of less than 10 years. This stark contrast suggests that whatever trade-off the short-lived bat species faced was surmounted by the long-lived bat species. The diversity of aging schedules in nature tells us that there are no absolute constraints or trade-offs. Similarly, there are no universal hallmarks of aging. Aged nematodes have fractured mitochondria, while aged humans do not. Humans develop lighter, gray hair as they age, while male giraffes develop darker hair as they age. There are no universal causes of death. Different animals die of different causes as they get older. Mice get cancer, while rats get heart disease. Pacific salmon poison themselves after reproducing with a burst of cortisol. There are no universal hallmarks of aging or universal causes of death, since aging is not a result of some universal constraint or trade-off. Instead, aging has been intricately shaped by evolution to suit the specific environmental demands of each species. Rather than being a consequence of some broad, uniform principle, aging has been directly selected for by evolution and has been finely tuned to the unique circumstances and challenges faced by each species. Understanding that aging is a consequence of evolved self-destruction pathways is a crucial perspective in the quest to develop effective therapeutics. This viewpoint underscores the importance of targeting the body's active pathways and targeting the body's timing mechanisms as strategies to combat aging. Nevertheless, this perspective is shunned because of people asking why. Why would evolution select for self-destruction? One theory is that aging is a group-selected population control mechanism. A second theory is that aging is a kin-selected pathogen control mechanism. A third theory is that aging increases the rate of evolution, regardless of the level of the unit of evolution. Perhaps our genes did build our bodies as vehicles for their own propagation, and those genes simply prefer not to have old cars on the road. Our current understanding is not close to confirming or rejecting any of these theories, just as our current understanding cannot explain why positive and negative particles attract each other. That is okay. The universe may never make sense to us. Nonetheless, science empowers us to create models, to innovate, and to develop anti-aging therapeutics without comprehending the nature of the universe. Observing the universe as it is, hypothesizing, and experimenting allow us to harness the universe's principles for practical purposes, without any real understanding. In general, the only things that make sense to us are those things which are specifically programmed into our biology. And an understanding of aging and evolution are not programmed into us. Consider, for example, the discovery of the complex numbers. The square root of -1 is the number x, such that x multiplied by x is equal to -1. This number is denoted by the letter I. A positive number times a positive number is positive, and thus I cannot be positive. Similarly, a negative number times a negative number is positive, so I cannot be negative. I cannot be positive or negative and therefore does not exist on the real number line. However, I exist nonetheless. I exist just as the numbers 1 and 2 exist. An understanding of the real numbers is programmed into our bodies. The complex numbers like I are not programmed into our biology and thus seem unintuitive. But the complex numbers exist nonetheless. The language of the universe is never going to be intuitive to you. You must train yourself not to be biased by what you feel makes sense. You must train yourself to overcome your programming or else you will die. Almost all animals have some understanding of the real numbers programmed into them. For example, when an ant leaves its colony, it counts its steps. If you put it to sleep when it's away from its colony and glue stilts on its legs before sending it on its way home, the ant will overshoot the colony on the return journey precisely in proportion to the length of the stilts. This is because the ant is counting its steps to determine the distance home. The ant may not consciously understand the counting numbers in the same sense that you are conscious of them, but it does understand them intuitively just as you do. Other numbers exist in the same way that the counting numbers do. These other numbers seem less intuitive to you since an understanding of them is not programmed into you the same way that the counting numbers are programmed into you. But they exist nonetheless. In order to demonstrate the existence of I, we must discuss the series of great observations that starts with the ancient paradox of the straight line. The paradox of the straight line, or Zeno's paradox, refers to the apparent contradiction that moving from a point A to a point B is an impossibility, as it requires an infinite number of tasks. If one starts at a point A, then before one can arrive at B, he must first arrive halfway there. And before he can arrive halfway there, he must arrive a quarter of the way there, and so on ad infinitum. This, however, is no contradiction, but rather the observation that the sum of 1/2 to the n, with n varying from 1 to infinity, is equal to 1. The sum doesn't approach 1, it equals 1, just as 1 and 1 equals 2. The paradox of the straight line is no paradox at all. Rather, it is the important observation that finite numbers can be equal to countable sums. Just as the unit square can naturally be thought of as the union of infinitely many squares of area, 1/2 to the n for each counting number n. In the same way, many functions can also be equal to the countable sum of monomials locally. This is the heart of Taylor's theorem, which states that for every real-valued function, f of x, and every real number, a, there exists a positive constant, r sub a, and constants c sub n, such that f of x is equal to the sum of c sub n times the quantity x minus a to the n, with the n varying from 0 to infinity, when the norm of x minus a is less than r sub a. One implication of Taylor's theorem is that polynomials spread out in all directions equally. The convergence of such an infinite sum of monomials is on the symmetric interval a minus r sub a plus r sub a. The power series sum clearly increases in absolute value as x moves away from a, and the rate of this increase only depends on x's distance from a. That is, the infinite sum will spread out in both directions of the real line at the same rate. This r sub a is called the radius of convergence of f at a. On its radius of convergence, the polynomial representation of analytic f is unique. Hence, there must be some formula that computes the radius of convergence in terms of the coefficients of the infinite polynomial. This formula is known as the Koshi-Hadamard formula. Now, let's consider the function f of x equals 1 over 1 plus x squared, which is analytic at every real number. Consider the radius of convergence of the Taylor series of f of x at a equals 10. By the Koshi-Hadamard formula, the radius of convergence is the square root of 101. Hence, the series converges at every real number in the interval 10 minus square root of 101, 10 plus square root of 101. Similarly, the radius of convergence of the Taylor series of f of x at a equals 100 is the square root of 10,001 by Koshi-Hadamard. Hence, the series converges at every real number in the interval 100 minus square root of 10,001, 100 plus square root of 10,001. Similarly, again, the radius of convergence of the Taylor series of f of x at a equals negative 100 is also the square root of 10,001 by Koshi-Hadamard. Hence, the series converges at every real number in the interval minus 100 minus square root of 10,001 minus 100 plus square root of 10,001. As the center of the series moves away from 0, the radius of convergence of the power series representation grows larger. However, the interval of convergence always ends beginning at some point near 0. There seems to be something near 0 that consistently prevents the power series of 1 over 1 plus x squared at some center a from converging. However, 1 over 1 plus x squared is defined at every real number. The only points where 1 over 1 plus x squared is not well behaved are the square roots of negative 1. Thus, plus and minus I must be the numbers preventing the power series of 1 over 1 plus x squared from converging. Furthermore, plus and minus I must be exactly 1 unit away from 0, square root of 2 units away from 1, and so on. Thus, the complex numbers form a plane over R. Just by considering polynomials over R, we have thus discovered that there is a plane of numbers over R, the complex plane. This is not a construction of the mathematician's imagination. This is not a model that happens to be good at describing our universe. This plane exists in reality. In reality, there exists a plane of numbers over R. Not a torus of numbers, not a sphere of numbers, but a plane of numbers over R. We have just observed its existence by considering the Taylor series of 1 over 1 plus x squared at various centers. Evolution has given us a biological understanding of the real numbers. Someday, it may give us organisms on Earth a biological understanding of the complex plane, or many more of the numbers outside even this plane. Why didn't evolution give us a biological understanding of C? It could have, but it didn't. Evolution also could have built us with a base 2 or a base 5 genetic code, but it didn't. The genetic code is base 4. Evolution could have used both left and right-handed amino acids for building proteins, but it didn't. Evolution could have given us bodies that are trying their best to survive, but it didn't. Evolution is currently beyond our understanding. Rather than dwelling on the why, it is more fruitful to focus on the how. The how aging happens is active self-destruction. Once we realize aging is a process of self-destruction, we also realize that the body possesses a deep understanding of its own age and when to initiate the self-destruction aging process. The aging as active self-destruction theory prompts us to explore the mechanisms behind the body's internal clock. A striking example of internal clocks can be found in female giant pandas. Female giant pandas have a unique reproductive pattern, with a very short window of fertility lasting only 2 to 3 days each year. This brief breeding period is not influenced by external factors like temperature or photoperiod. Rather, it is governed by an internal circannual oscillator, much like the circadian oscillators found in almost every human cell. The panda's internal circannual clock regulates its reproductive hormones to ensure that they can only conceive during this limited time frame. This example demonstrates that the body can use long-term clocks in order to decrease its own individual fitness. There is some evidence that the mammalian brain has a clock built into a neuroendocrine organ called the hypothalamus. The hypothalamus keeps time for daily cycles of sleeping and waking, and it may have a role in programming puberty and aging as well. The notion of aging being governed by long-term clocks warrants dedicated research. We must unravel how these clocks operate and discover whether they can be reversed. There is already some evidence that the body has the ability for self-repair when it's prompted to believe it is younger. In favorable environments, the nematode C. elegans develops rapidly and has a lifespan of 20 to 30 days. In adverse environments, however, this worm enters into a state of dormancy called the dour state, in which it can remain for months, multiple lifetimes for a C. elegans. If, while in diapause, the nematode senses the return of a favorable environment, it resumes its normal life course of 20 to 30 days. Diapause in worms suggests that turning back these clocks can erase hallmarks of aging. Mitochondrial fission of dour C. elegans, for example, is reversed when the nematode exits the dour state. Favorable environments reduce lifespan because the body is not trying its best to survive. However, if the body's aging clocks are reversed, the body may be fooled into returning the organism to a healthy state. Aging research should focus on figuring out how the body's clocks work, and how these clocks can be turned back. You might believe that you only need a mere century to live a fulfilling life, but you have not internalized what you are giving up. Your decision to devote your energies to whatever cause you feel so passionate about was rooted in the misconception that you only had 100 years to sacrifice. No wonder so many men have marched off to war. They were only throwing away 80 years. But you live in an exciting time. You could be part of the generation that cures aging. Your entire worldview is based on the false belief that your body must be dirt in 100 years. This is a falsehood. Here is the crucial realization. Your 1,000-year-old body could have the same probability of mortality as your 20-year-old self. With enough societal prioritization, we can be the last generation born on the clock.